In this video, we'll talk all about one example. And that example is going to come from an extension that is the splitting field of a polynomial that we've talked about before. So let's take x cubed minus 2. This is an irreducible polynomial in q bracket x. It has three roots in c, cube root of 2, zeta 3 times cube root of 2, and zeta 3 squared times cube root of 2. And what do I mean when I write cube root of 2? I mean this positive real number that cubes to 2. And what do I mean when I write zeta 3? This is a primitive third root of unity. I'm going to pick the particular one that is e to the 2 pi I over 3 minus 1 plus square root of minus 3 over 2. This has minimal polynomial over q, x squared plus x plus 1. What's the other root of this polynomial? Well, if you square zeta 3, you get minus 1 minus square root of minus 3 over 2, which should be minus 1 minus zeta 3. And why is that? Well, zeta 3 squared plus zeta 3 plus 1 equals 0. So zeta 3 squared has to be equal to negative zeta 3 plus 1. So you can check that all of this is true. This is a splitting field that we've talked about before. If you take the field generated over q by cube root of 2 and then another one of these roots, say zeta 3 times cube root of 2, then you must also contain the third root, because if you contain these two elements, you contain their quotient, which is zeta 3. And then if you contain zeta 3 and you contain cube root of 2, you contain zeta 3 squared times cube root of 2. So you contain all of the roots. We've seen before that the degree of this extension over q is 6. OK, so what are we seeing? This is a field generated over q by these two elements. So in particular, we can represent elements of this extension as polynomials in these two elements. And we see that if you have sigma being an automorphism of k fixing q, it's determined by where it sends the cube root of 2 and where it sends zeta 3 times the cube root of 2. And what do we know about where sigma has to send these elements? Well, it sends a root of x cubed minus 2 to another root of x cubed minus 2. So there are three choices for where to send the cube root of 2 and three choices for where to send this other root as well. So you might think like, well, OK, there's at most 9 possibilities for sigma. But using what we've proven already, it's not just that sigma sends roots of x cubed minus 2 to roots of x cubed minus 2. We prove something better, which is that sigma gives a permutation of these roots. So it's not possible for sigma to send each of these two different roots to the same place, for example. OK, so it gives a permutation of the roots of x cubed minus 2 and k, permutation of these three elements. And if I tell you which permutation of those three elements sigma gives, then that certainly says what does sigma do to cube root of 2 and what does sigma do to zeta 3 times cube root of 2. So we know all of sigma. So how many possibilities do we have for sigma? Well, we have as many possibilities as we have permutations of the roots of x cubed minus 2 and k. It's not clear that any one of those permutations gives an automorphism of k. But we do see that there's at most 3 factorial, 6 possibilities. But we know that k is the splitting field of a separable polynomial in q bracket x. So the number of automorphisms of k fixing q is the degree of k over q is 6. So there are at most 6 possible automorphisms. The degree is 6. This extension is Galois. So in fact, there are 6 automorphisms of k fixing q exactly. And every one of these 6 permutations of the roots of x cubed minus 2 and k gives rise to an element of the Galois group. So each one of these 6 possibilities really does give an element of this Galois group. OK, so what is that telling us? The Galois group has order 6. But we know more. This Galois group is isomorphic to S3 because its elements are described in terms of permutations of 3 things. So this is a group of all permutations of 3 elements. What are those 3 elements? They are the 3 roots of x cubed minus 2 in k. So because this Galois group is described in terms of the permutations of 3 elements, we know that it is isomorphic to S3. Okay, but this description doesn't make it really clear how to actually write down what an element of the Galois group does to an element of K. So now let's think about this example in a different way. It is true that K is the field generated over Q by cube root of 2 and zeta 3 times cube root of 2. But you can give maybe a nicer description of K as the field generated over Q by cube root of 2 and zeta 3. So an element of the Galois group is determined by where it sends cube root of 2 and where it sends zeta 3. And now, what are the possibilities for where to send cube root of 2? You have to send it to another root of x cubed minus 2 in K. So either cube root of 2, zeta 3 times cube root of 2, or zeta 3 squared times cube root of 2. And where can you send zeta 3? You have to send it to another root of x squared plus x plus 1. So either to zeta 3 or to zeta 3 squared. And now there are at most 6 possibilities. And each one of these 6 possibilities, you make a choice for where to send cube root of 2. You make a choice for where to send zeta 3. Each one of these 6 possibilities really does give an automorphism of K that fixes Q. So this really does give an element of this Galois group. So I'll pause and erase. We'll write down 2 particular elements of this Galois group. And by taking powers and products of those elements, we'll see how to describe the entire Galois group in terms of those 2 particular elements. We know that we have 6 elements of this Galois group of K over Q, and that each element is determined by what it does to cube root of 2 and what it does to zeta 3. So let's name sigma in this Galois group to be the automorphism of K fixing Q that sends cube root of 2 to zeta 3 times cube root of 2 and zeta 3 to zeta 3. And let tau be the element of the Galois group that sends cube root of 2 to cube root of 2 and zeta 3 to zeta 3 squared. So I first want to show that it really is enough to say where an element sends cube root of 2 and zeta 3 in order to understand if we know those 2 values, then we know where it sends any element of K. And how do we see that? Well, we know how to describe a basis for K over Q. One basis for K over Q is a 6-dimensional vector space over Q is 1 cube root of 2 squared, zeta 3, and then zeta 3 times cube root of 2 and zeta 3 times cube root of 2 squared. All right, so every element in K is a plus b cube root of 2 plus c cube root of 2 squared plus d zeta 3 plus e zeta 3 times cube root of 2 plus f zeta 3 times cube root of 2 squared for some a, b, c, d, e, f in Q. So what does sigma do to such an element? Well, it's an automorphism of K, and it fixes Q. So you can write it as sigma applied to each term in the sum and then add those together. And sigma sends a to a, b to b, c to c, d to d, e to e, and f to f. So we get is a plus b times sigma of cube root of 2, which is zeta 3 times cube root of 2, plus c times zeta cube root of 2 squared, which is zeta applied to cube root of 2, and then square that. So we get zeta 3 times cube root of 2 squared. Yeah, I have the square outside here. Great. Then we get d zeta 3 and e zeta 3 times sigma of cube root of 2, which is zeta 3 times cube root of 2. And then for the last one, we get f times zeta 3 times sigma cube root of 2 squared. OK, we want to rewrite this element in terms of our original basis. And our original basis doesn't have any zeta 3 squareds in it. But we know that zeta 3 squared equals minus 1 minus zeta 3. So all we're doing in this next line is everywhere we have a zeta 3 squared, we're replacing it with minus 1 minus zeta 3. So we have one here. We have one here. E minus 1 minus zeta 3. cube root of 2. And then at the end here, we actually have a zeta 3 cubed, but that's just 1. So that goes away. So we get f cube root of 2 squared. Now we group together like terms and we rewrite this in terms of our original basis elements. So we have a minus e cube root of 2. The only place that a cube root of 2 by itself appears here is not here, not here, not here. Here we get a term that is e times minus 1 times cube root of 2. So we get minus e cube root of 2. And that's it. Plus, OK, grouping together, now you can see how this goes. You get f minus c cube root of 2 squared plus d zeta 3 plus b minus e zeta 3 cube root of 2, and then plus minus c zeta 3 times cube root of 2 squared. OK, so by describing what sigma does to each of these two special elements, we know what it does to any element in K. And you could do something very similar for tau or for any other element of this Galois group. So what are these other elements of the Galois group? Well, there are 6 choices for where to send zeta 3 and where to send zeta 3 and where to send cube root of 2. So let's just go through each of those choices. So we've done 2 of them here. The identity is the automorphism you get by sending each thing to itself. Sigma squared sends cube root of 2 to zeta 3 squared times cube root of 2 and zeta 3 to zeta 3. Tau times sigma sends cube root of 2 to zeta 3 times cube root of 2 and zeta 3 to zeta 3 squared. So let's just think about that one. So what happens? Sigma first sends cube root of 2 to zeta 3 times cube root of 2. Zeta 3 goes to zeta 3. And then you apply tau. And tau sends zeta 3 to zeta 3 squared. So this part checks out. And sends, well, where does it send zeta 3 times cube root of 2? It sends the cube root of 2 to itself. And it sends zeta 3 to zeta 3 squared. So this works also. OK, tau times sigma squared. Similarly, you can see that that sends cube root of 2 to zeta 3 cube root of 2, zeta 3 times zeta 3 squared. And now we've seen that we've gone through all 6 possibilities for where to send these 2 elements. But you can compose these automorphisms, these elements of this Galois group. And sigma times tau, this is some element of the Galois group. But which one is it? So if you want to figure that out, you should just see what sigma tau does to cube root of 2 and what it does to zeta 3, and then see which of these 6 possibilities it matches up with. Because if you have 2 elements that do the same thing to cube root of 2 and to zeta 3, they do the same thing to any element of K. OK, so sigma times tau. So tau first sends cube root of 2 to cube root of 2, and then sigma sends cube root of 2 to zeta 3 times cube root of 2. Tau sends zeta 3 to zeta 3 squared, and then sigma sends that zeta 3 squared to zeta 3 squared. So where do we see this before? Sigma tau equals tau sigma squared. OK, so we're seeing relations among these group elements. So here's one. It's easy to see that sigma cubed is the same as tau squared as the identity. This Galois group is a group of order 6. It's generated by tau and sigma, and it is isomorphic to S3. OK, so we already knew that this Galois group was isomorphic to S3 because it was a group of permutations of these 3 roots of x cubed minus 2 in this field K. But now we have this really explicit description of what all these elements of the Galois group are and how to multiply them together and what they do to elements of K. So the last thing I want to do in this video is we have this Galois group. And for each subgroup of this Galois group, we can write down the fixed field. And we'll have this diagram of subgroups, and we'll get a corresponding diagram of subfields of K. We now have a nice description of this Galois group of K over Q. And now for each subgroup of this Galois group, we can compute its fixed field. So to do this, I wanted to leave up this computation of what sigma does to an element of K. Because now we can see what it means for an element of K to be fixed by sigma. if you're an element a plus b cube root of 2 plus c times cube root of 2 squared plus d zeta 3 plus e zeta 3 times cube root of 2 plus f zeta 3 times cube root of 2 squared, and you're fixed by sigma, that means this element is equal to this element here. So in particular, each of the corresponding coefficients has to match up. So b equals negative e. The coefficient of cube root of 2, when we write out these two elements in terms of this chosen basis for k over q, they have to match up. They have to be the same element. So b equals minus e, c equals f minus c, d is d, that doesn't say anything, e equals b minus e, and f equals negative c. But now, okay, if b equals minus e, then e equals b minus e means e equals minus e, so 3e equals 0. But e is a rational number, so that means that e is 0. And that means that b is 0. Same idea exactly. F equals minus c, 3c equals 0. So c equals 0, and f equals 0 also. So what are the elements that are fixed by sigma? They're the ones where e, b, f, and c are 0. So that is the set of all things of the form a plus d times zeta 3, where a and d are elements of q. But this is the field generated by zeta 3 over q. So what are we really talking about? For each subgroup of the Galois group, we want to compute its fixed field, not for each element of the Galois group computing its fixed field. So if you have an element fixed by sigma, it's easy to see that it's automatically also fixed by sigma squared. Because you apply sigma, you get back the same element. You apply sigma again, you get back the same element. So what are we seeing? We're seeing that the fixed field of the subgroup of the Galois group given by the identity sigma and sigma squared is the field generated over q by zeta 3, q adjoins zeta 3. So I'll pause and erase, and the last thing I'll do in this video is draw the diagram of subgroups of this Galois group and the corresponding diagram of fixed fields. Let's look at all the subgroups of the Galois group of k over q. We know that this is generated by sigma and tau and is isomorphic to S3. We have the trivial subgroup at the top. So trivial at the top, the whole group at the bottom, the smaller subgroups are drawn higher up here. So the subgroup generated by tau, the one generated by tau sigma, the one generated by tau sigma squared, these all have degree or order 2. The subgroup generated by sigma has order 3. So this is bigger, this comes a little lower down. We can compute the corresponding fixed field of each of these subgroups. The fixed field of the identity subgroup is the whole group K. The fixed field of the whole group of automorphisms of K fixing Q is all of Q. And the only other one we've seen is the fixed field of the subgroup generated by sigma is Q adjoins zeta 3. So I'll leave it to you to check that these other three fixed fields are correct. The fixed field of the subgroup generated by tau is Q adjoin cube root of 2. Then we have these other two. So we have this correspondence in this diagram. We have the subgroup diagram of this Galois group, but inverted with the whole group at the bottom, trivial group at the top, and then this corresponding diagram of subfields. There are other things we can look at in this diagram of subfields and ask, do they correspond to things going on in this diagram of subgroups? For example, this extension, Q adjoins zeta 3 over Q, is a Galois extension. It's a quadratic extension of a field of characteristic 0. But this extension, Q adjoin cube root of 2 over Q, is not Galois because there are not enough roots of the polynomial x cubed minus 2 in this field. So this extension is Galois. This extension is not. What is different about the corresponding subgroups of the Galois group? In one case, we have the subgroup generated by sigma, and in the other case, we have the subgroup generated by tau. And one thing that's different about them is that the subgroup generated by sigma is a normal subgroup of this Galois group. And the subgroup generated by tau is a subgroup, but it's not a normal subgroup. So these types of statements are going to be explained by the fundamental theorem of Galois theory, which we'll come to in the next lecture or two.